It is MECH 2210 tutorial again, and I would say this topic has really high chance to be on your exams. This tutorial illustrates you the most common way to solve this kind of problem by using two examples. The most common way is to have a moment of inertia table and plug in the values into the two formulas. I assume Globus has already told you guys how to find this moment of inertia. No derivation is included in this video, but I will make another video for derivation and direct integration method if I have time. So let's look at an example. This problem is extracted from review problems of the textbook. It is available online. Let's look at this problem. It's rather tempting for us to think that the air pressure is just in a square part, and summing the hydrostatic force in the bottom gives the magnitude of the resultant force. But this is totally wrong. Let's pick a point here. Yes, this point has 40 kilopascal. But this point, it has 40 kilopascal plus gamma times 4 meter. And if we sketch pressure distribution on the side wall, it's going to look like. So we may think that the air pressure is acting throughout the area, and we can break the force into hydrostatic component and air pressure component. So let's just calculate the hydrostatic component of the force with the formula that I put down here. But there is a problem. There is no trapezium in this table. How can we locate the center of the trapezium? One way to do this is to break this into two parts, a rectangle and a triangle. By doing this, we can locate the center of each and calculate the force on each section. Then we can add them up later together. Let's label section 1, 2, 3 first. Now the center is here, halfway of the 4 meter. So the center of the rectangle is 2 meter below the liquid level. And then for the triangle, this length is 1/3 of the height. And this is 4 divided by 3 meter. So for the triangle, the center is 4 meter minus 4 divided by 3 meter equals 8 divided by 3 meter below the liquid level. Now we calculate the area of each section. For the rectangle, A1 equals 4 times 2 meters square, and that is 8 meters square. For the triangle, that is 2 times 4 divided by 2 equals 4 meters square. So now we use this formula for both the rectangle and the triangle. For the rectangle, and that is about 100 and something kilonewton. For 2, for the air pressure component, we have to consider all sections 1, 2, 3. So A equals A1, A2, A3. That is 60 meters square. So we have air component to be dA, that is 40 K times 16. And total force and we are done with this example. We look at one more question concerning pressure center and we end today's video. We shall draw some problem sketches for this problem, since the problem statement is going too long and it is hard to construct such a complicated image in your mind. So we draw the triangle first and we label the length. A equals 2 meter, B equals 2.5 meter, and we sketch how the whole thing looks like. So this is the base, and this is our triangle viewed from the right, and then this goes up, and say this is the water level, and we set a coordinate system here. This is y axis, and this is going 60 degrees. The water depth is 6 meters. The center of the triangle is A divided by 3 above the base, and the center in this figure is about here, and this is A divided by 3. So this length is YC, and YC equals 6 divided by sine 60 and minus A divided by 3. So that is 6.09 meter. And then HC equals YC sine 60. So that becomes 5.7283 meter. And we find the area of the isosceles triangle is AB divided by 2. So that is, and we plug in the value into the formula gamma HCA, and that is 12.5 K times and we punch in the calculator to find. But the question also asks for pressure center. By symmetry, if this is our isosceles triangle, then the pressure center lies along this line, directly below the centroid. You can verify that the centroid must lie along this line by using the formula and setting an arbitrary x coordinate for the centroid. Also, it must be below the centroid, since the bottom particles experiences a larger hydrostatic pressure. To locate the pressure center's y-coordinate, we have to find IXC, the moment of inertia about x-axis at the centroid first. From the table, we find that IXC equals BA cubed divided by 36, and that is 2.5 cubed 36. That is 0.86806 meter fourth power. Note that its unit is meter to the 4. So we plug in the formula and find that YR equals plug in the value of YC, and that equals, we have already schematically shown that how it looks like, and that is around here. But why shall we study pressure center? It is for calculating moment. This is rather important. If our isosceles triangle is hinged at the bottom edge, so we add a hinge here, and we also have the hydrostatic force acting at the pressure center, so we can calculate the moment arm to be. So the moment produced by the force equals FRD equals since there is a moment here, we must add some mechanism to prevent water to flow out if there is a hinge here. But if we hinge the triangle at the pressure center, then this force, the hydrostatic force, will produce no movement. So we don't need such a mechanism. So today we talk about how to use the formula and inertia table to find the hydrostatic force on a plane surface, and how to find the pressure center, and how to use that to find the moment. We also went through 2 examples to illustrate these skills. Actually, the concept of pressure prism is just a special case when we consider the section area to be rectangular. I will only make an extra video about that if I have time. So thanks for watching, and feel free to ask us any question and give us any feedback in the comments.